The equations that we were looking at in the last section were all linear equations. All of the exponents on both x and y were 1. What if we have equations that are nonlinear? What if we have a parabola and a line? What if we have a parabola and a circle? We could have lots of different combinations of equations that are nonlinear. We're still looking for the points of intersection as the solutions of those systems because we want to know what points are on both equations. So that's what we're looking for in this section. We are going to use our same two methods that we used for linear systems, addition and substitution. We could look at them graphically. We're not going to spend a ton of time on that, but because you can see them, but they're not always nice, pretty numbers. So that's why we're looking at the algebraic methods more. Here's an example. Suppose the area of a rectangle is known to be 12 square feet and the diagonal of the rectangle is known to be 5 feet. If the length of the rectangle is L and the width is W, that will lead us to L times W is 12, right? That's area is 12. And the hypotenuse, if we have a rectangle, and the hypotenuse is known to be 5, and this is length and width, then L squared plus W squared will equal 5 squared by the Pythagorean theorem. Neither one of those is a linear equation because you have a product of the two variables in the first one, and here you have a square on your two variables. Neither one of those is going to be a line. That's what we're working with here. We still use the same methods, substitution and addition. One thing we do want to know is the general form of the equation of a circle, just so we can recognize a circle when we see it. This is the general form of a circle. We are going to talk about circles much more extensively in Unit 7, but here I wanted to give you this equation. X minus h quantity squared plus y minus k squared is equal to r squared. Center is hk, radius r. That's actually this thing right here, right? Where the center is 0, 0. The h and the k are both 0, and the radius is 5. Let's use this idea to help us, these ideas that we have to solve this system of equations. The first equation here is a circle centered at the origin with radius equal to 5. The h and the k are both 0. The r squared is 25, so r is 5. This is a line. If we think about what we could have as far as number of solutions to this, we could have 2 if the line crosses the circle, right? So we have the circle, suppose we have this line, whatever. You could have 2 points of intersection here and here. That's just a rough sketch. That is not what these look like. But you could have 1 solution if the line just touches at one spot, or you could have 0 solutions if the line is out here and never intersects that circle. So we're not sure how many solutions we have to this, but it could be 0, 1, or 2. In this case, the addition method will not work because there's no like terms in the first equation and the second equation, right? I can't multiply the first equation by a constant or the second equation by a constant and have that eliminate, have opposite coefficients on the same type of term. This is an x squared, that's just an x. So that's not going to work. We are going to have to use substitution here. That means we need to solve for one of the variables. I'm going to solve for x to give me 4/3 y. It doesn't matter which one you solve for, but it does matter that you use the second equation to solve for x or y. If you tried to solve for x or y in the first equation, you're going to have a plus, minus, and a square root, and it just gets yucky. So choosing what you solve, which equation you use, and what variable you solve for is critical. I'm going to take that and substitute it right in there. So I get 4/3 y squared plus y squared equals 25. Cleaning that up gives me 16/9 y squared plus y squared equals 25. I'm going to write that as 9/9 y squared so that I can combine those to 25/9 y squared equals 25. Multiply both sides by 9/25, the reciprocal of what we have there, to give us y squared equals 9. That tells me y equals plus or minus 3. Let's start with the solution y equals 3. Remember, x is 4/3 y. So x is 4/3 times 3, which is 4. So we get the ordered pair 4, 3. And we also get a solution when y equals -3 of x equals 4/3 times -3, or -4. So I get the ordered pair -4, -3. My picture here then is going to be something like this. It's not exactly like that because I drew that line backwards, right? It's actually, the line's going to be, you know, over here where it intersects at 4, 3 and -4, -3. That's the type of picture we would actually get instead of the line going the other way. So, but we didn't really know that until we got that algebraic. We could graph them and we could see, but again, it's not necessarily, the graph is not necessarily going to tell us, because this circle, it's really hard to see what points that circle goes through other than, you know, the 4 corners of the circle. All right, so we have 2 points, 2 solutions there. This one is an ellipse and a what we call a hyperbola. That we could have up to 4 solutions. We are going to see both of these in Unit 7, so hang tight for that and you'll know how we get there. This one I think is easier to solve using the substitution, the elimination method, because I don't want to solve for x or y in either of these equations, and they do have opposite coefficients, same degree, so I can make the opposite coefficients. I can make that 15x squared minus 5y squared equals -5. And then if I bring the other equation down, 2x squared plus 5y equals 39. 5y squared. When I add those, I get 17x squared is equal to 34. That means x squared is equal to 2. So x would be plus or minus the square root of 2. I can pick either equation to find the y. I'll probably pick this one, 3x squared minus y squared equals -1, just because the numbers are a little smaller, but it doesn't really matter. Whichever one of these I put in, the x squared is always 2, so I'm going to just replace the x squared with 2 and come up with my solutions, and just recognize that this works for x equals √2 or x equals -√2. 6 minus y squared equals -1. Negative y squared will equal -7. So y squared equals 7. which tells me y equals plus or minus root 7. For each of these x values, for x being root 2, I got the square root of 7 and negative root 7. For x being negative root 2, I got y equals root 7 and y equals negative root 7. Because it didn't matter. When I plugged in x equals root 2, I got 2 solutions. When I plug in x equals negative root 2, I get 2 solutions. So total, I have 4 solutions here. I'm not going to give an exact picture of this, but an ellipse is like an oval. So let's suppose we had, you know, an oval like this or something like that. A hyperbola is going to look kind of like this. That's where you get your 4 solutions. Here, 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 and here. It almost looks like a baseball, doesn't it? I love it. Baseball's back, baby. Okay. One more example. This is a couple of hyperbolas, actually. But again, I don't expect you to know that yet. We are going to see that in Unit 7. It doesn't really matter. One good thing you can use that's a fun, nice tool to check these things is something like Desmos.com, because Desmos will graph things that aren't functions. Neither of these is a function. They don't pass the vertical line test. You can see that if you plug in a single value for x, you're going to get 2 y's in both of these equations because of that square on the y. So, and we saw that, right? We plugged in a single value for x, we got 2 y values. So not functions. So you can't really graph those in your graphing calculator. You can, but it's a lot harder than it needs to be when you can just go to something like Desmos.com, which is DESMOS.com, and you can graph in there anything. It doesn't have to be a function to graph it. You just type it right in. I think I showed you that on one of the earlier videos, Desmos. This last example here is going to be best solved using substitution, where we let y equal 3 over x and plug that in right there in place of y. X squared minus 3 times 3 over x squared equals 6. X squared minus 3 times 9 over x squared will equal 6. That gives x squared minus 27 over x squared equals 6. I don't like that x in the denominator, so I'm going to multiply both sides of this equation by x squared, which gets me to x to the 4th minus 27 equals 6x squared. I really like having equations equal to 0 if possible. Not always required, but sometimes very helpful. So I am going to move that 6x squared over. This is an equation of the quadratic type, where because I have x to the 4th and x squared, I'm thinking this is going to factor in, hopefully it'll factor into x squared and x squared. And I'm looking for 2 numbers that multiply to give me negative 27 that add up to negative 6. That's going to be negative 9 and positive 3. If you think about distributing this out, you get x to the 4th plus 3x squared minus 9x squared. Those two will combine to give me the negative 6x squared minus 27. Let's set those factors equal to 0, or you could factor further if possible. This one factors further. X minus 3 times x plus 3 equals 0. Gives you x equals 3 and x equals negative 3. This one tells you x squared is negative 3, which is not a real number. That would be imaginary numbers. Can't have x squared equal to a negative. I have these 2 solutions. when x equals 3, I think the best thing to do is use y equals 3 over x. So 3 over 3, or 1. And when x equals -3, I get y equals 3 over -3, which is -1. So I get this ordered pair 3, 1, and the ordered pair -3, -1 are solutions to this system of equations. So substitution works there. Addition really only works if you have the same variables with the same exponents, at least one of them. You have to have the same exponents so that you can get opposite coefficients on that. Okay, let's look at this application here. Between 1990 and 2013, there was a drop in violent crimes and a spike in the prison population in the United States. The violent crime rate can be modeled by the quadratic equation y equals 0.6 x squared minus 28x plus 730. Imprisonment rate can be modeled by the linear equation -15x plus y equals 300. Let me be really clear about where these equations would come from. What analysts do, what mathematical modelers do, is they look at the data and then they try to find the best fit of that data. They try to find the equation that best fits it. It doesn't mean that every point, every real life data point is going to be exactly on this parabola or exactly on this line, but it does mean that these equations best fit the data and are reasonable to work with. Lines are very reasonable to work with. So remember, we saw that scatter plot way back a long time ago. That's really what's happening here. These imprisonment rates would be put on a scatter plot and then look at that and say, oh, if it's a line, I want to find the equation of the line that most closely represents those data points. And same thing for this. If a quadratic came up, that means it was a parabolic shape in the data. And so they chose to use a quadratic equation to model that parabolic shape. Each function, x represents the number of years after 1990, y represents the number per 100,000 Americans. Solve the nonlinear system of equations and interpret the results. I am pretty confident that you can solve this system. The important part to me is interpreting the results. What do we get? I'm going to say y equals 15x plus 300, and I'm going to take that and substitute that in for this y. So I get 15x plus 300 will equal 0.6x squared minus 28x plus 730. Now I have a quadratic equation in just one variable, which I typically want set equal to 0. Let me do this. I want to subtract 15x from both sides, and I want to subtract 300 from both sides. That gives me negative 43x plus 430. It is possible that this equation factors. I really don't like the decimal in there, so one thing you can easily do is multiply both sides of this equation by 10. Doesn't really matter, I just prefer to work with non-decimals, right? Let me write this here so you're clear what I'm doing there. Multiply this side by 10, multiply this side of the equation by 10, and that gets rid of that decimal. 0.6 times 10 is 6. Let's go ahead and I'm going to use a quadratic formula. I could play around with it and maybe make it factor, but I don't think it's a wisest choice here. Opposite of b plus or minus square root of b squared. So 430 squared minus 4 times a times c. all over 2 times A. $430 squared is 1. Oopsie, there technically should be a negative here. It doesn't really matter because when you square it, you get the same result. 184,900 minus let's put that in. 4 times 6 times 4,300 is 103,200. I was getting a little nervous there. I was thinking that number might be super big and bigger than what we got. I don't want a negative inside that root. 184,900 minus that answer is 81,700 all over 12. I'm going to go ahead and approximate this here because we're talking about real life data. So let's go ahead and do that at this point. 285.83 all over 12. What is the question here? Solve the nonlinear system of equations and interpret the results. Let's go ahead and find these two values. I'm going to take that 285.83 that I have still in my calculator, add 430 and divide by 12. That gives me 59.65. Or if I do 430 minus the 285.83 and divide by 12, I get 12.01. Let's go up and reread our question, reread what this X represents, and see what makes sense here. X represents the number of years after 1990. In this case, so we're talking about 60 years after 1990 would be the year 2050, or the year 2002, right? 12 years after 1990. Notice that these equations really only should be used to model data between 1990 and 2013. These are the years that were studied to give you these equations. To go to 2050 would be quite the stretch. So I'm thinking we need to be talking about this year here. And then the y value, let's do this. Y equals 15x plus 300. Y equals 15 times 12 plus 300 gives me 480. Let's talk about the interpretation of that. Y represents the number per 100,000 Americans. Well, in one of the equations, the Y is talking about violent crimes, right? Violent crime rate. So we are saying let me write it up here. In 2002, the violent crime rate, and the imprisonment rates were equal at 480 people per 100,000 Americans. Remember, we solved this system, so we're talking about both of those being equal in the same year. That is the year the violent crime rate and the imprisonment rates were equal to one another. Cool. I like it. I like seeing application based on some real data. So in this video, we looked at solving systems of nonlinear equations, right? Here we were looking at a parabola and a line. We looked at circles, ellipses, hyperbolas, and you don't need to know what all of those look like. You don't need to be able to graph all of those at this point to be able to solve those systems. Because we've got our algebraic techniques that will give it to us. But like I said, it's helpful to see the picture sometimes, because then you know how many solutions to expect. In our next video, we're going to look at inequalities, linear and nonlinear inequalities, and then systems of nonlinear and linear inequalities.